Okay. Say we're go.
I'm good. I'm good.
We're going? Okay. All right, guys. First question. Who lives in a pineapple under the sea?
SpongeBob.
SpongeBob SquarePants. You know who else lives at the bottom of the sea? You and me. We all live at the bottom of the sea. Your feet right now are on the bottom of an ocean of air. The air goes 300 miles up until it hits outer space. That's what the top of the ocean of air. Does that make sense? Now think about that, guys. That air is matter. It has mass. And I'm going to put some dots on the table here with my finger. That's about a square centimeter right there, these dots that I'm making. Each of these dots is about a square centimeter. And try to imagine like a skinny column of air coming up from that fingerprint all the way to outer space. If you were able to lift that column of air up, it would weigh about 15 pounds. So for every square centimeter on your body, there's 15 pounds pressing on you, but it doesn't feel like it because you're used to it. Have you ever gone down deep in the pool and had it press on your ears? You're not used to that. That's why if you go really deep, it begins to hurt a little bit unless you kind of pop your ears. Well, what I'm doing is I'm going to heat some matter today. I'm heating this can. I'm heating a can. I'm going to go ahead and get this one heating too. So I'm heating a can. What's it made of?
Aluminum.
Aluminum. Here's aluminum. And I'm heating some water in it, just a little bit of water. Last week we did a little activity where we heated solid water until it boiled. At what temperature does water begin to boil?
100.
100 degrees Celsius. At what temperature does water begin to freeze? 32 Fahrenheit or 0 Celsius. Now, aluminum has a much different freezing point and boiling point. So you guys, I don't know if you can hear it or not, but can you hear in the Diet Coke can how the water is already boiling? But the aluminum can is still frozen. It's still a solid, right? Because they have different heating curves. Does that make sense? Now, there's air inside of that is also getting hot. Would you guys agree? And I have the cans are open. That's why they're not exploding. The cans are open. So what's happening to the gas that's inside of that can as I heat it? When things get hot, what do? They expand. And so can you guys see the gas expanding out? You can see some. That's true. But you can, because the water vapor is coming out, you can see that the gas is expanding. It's being carried out. That's a really good point. It's being carried out by the expanding gas, right? And that water vapor that you're seeing is actually condensing in the air and becoming what? A liquid again, because you can't see a gas. Very good. Good job, Corbin. Keep me honest. All right. Now, that air inside the can is expanding. Now, what would happen if I cooled it? What does it do? What's the opposite of expanding?
Condense.
Close.
Contract.
Contracting. It's going to contract. Well, what I'm going to do is I'm going to put this can in the water upside down so it can contract. Now, if I were to just cool off the can, the air would contract and go back into the can, right? What I'm going to do is put it in the water, this water upside down, so that when it tries to contract, instead of pulling the air back in as it contracts, it's going to try to pull the water in. And watch what happens to the can. Any predictions? None?
It's going to swim.
So, did it blow up or in?
In.
In. What pushed it in?
Air.
Air. The ocean of air on the outside, 15 pounds per square centimeter, crushed it in as it tried to contract and pull the water in. Does that make sense? Look, you guys want to see one more? Now, you could do this as extra credit at home. You don't have to have a burner. You can do it on your stove. If you have a gas burner and it won't fit on the stove, just put the can on a frying pan. Don't forget to use tongs. You probably have tongs for picking up corn. They may look different than this, but you have tongs at home. If you do this at home, I'll give you extra credit if you demonstrate it for your parents. And they send you a note. Ready? So it's a fun way to smush your cans for recycling. How many pounds per square centimeter? 15 pounds. Good. What I have here is a vacuum chamber. And I have a pump right here, and I can take the air out of this jar. This is called a bell jar. All right. And what I'm going to do is I'm going to show you how the air pressure can affect the heating curve of this matter. I have very warm water. It's just warm. Would I be able to put my finger in boiling water? No. And I'm going to put it inside this vacuum chamber. And I'm going to take all of the air pressure off. I'm going to put this cork in, and I'm going to suck the air out of this jar so that it will no longer have that 15 pounds per square centimeters on it. And I want you to watch what it does to the boiling point of the water in this container. So just watch it for a minute. Now, this is what would happen if water were to go into outer space. There'd be no pressure on it, and something would happen to it, depending on the temperature.
Isn't it floating around in space?
What's that?
Isn't it floating around in space?
Well, it also doesn't have gravity, but the gravity's still affecting it. Do you see how it's still inside the bottom of the cup? It still has gravity, but it's losing its air pressure. You guys see the bubbles beginning to form? And if we can get enough pressure off of it, we should be able to get it to boil. Either that or we may need to raise the temperature of the water just a little bit. Looks like Sprite, doesn't it? If I were to put Sprite in here, it has so much gas in it that it would actually overflow. But I don't have a Sprite, or I'd show you. If you think about it, remind me next week or next class and I'll do one. That'd be fun. Class, we'll do a Friday. You know what? I'm going to stop this. Go ahead and pause it there. The water's still not super hot, but it is warm. I'm going to stick it in here, and I'm going to lower the pressure. Watch what happens to the boiling point of this water. Hopefully. Yeah, it worked every class until you guys. It's going to work. Look at it. You see all the bubbles forming? Here it goes. Now, are we adding any heat? No. We're just changing the pressure.
Is that what you meant by altitude stuff?
Well, you'd have to get really, really, really high up in the air because the air is denser down here. So I'm not sure how high up you'd have to go to get that lower pressure. Probably close to outer space. 300 miles. Yeah. So it's pretty deep. You're pretty deep down here in the ocean. Is it beginning to boil for us? Come on.
You can do it, buddy. You can do it.
Come on, baby. Boil. No. Well, that gets warm, but not hot. It's not adding heat. It's just taking off the air. It comes out of the jar and up this tube. And if you feel right here, you feel air coming out? It's taking the air out of here. All right. Well, that wasn't too exciting. But did it boil a little bit? It did boil a little bit.
Did you do a full rolling boil in your other
Yes. You guys want to run the water for a little longer, Laney, and try one more time? Okay. So while we're waiting for the water to get a little bit hotter, we're going to see what would happen to your body if it were to lose pressure. If you were to lose that 15 pounds per square centimeter of pressure in outer space. When you're an astronaut, you go to space, you wear a spacesuit. Your body is full of liquids and gases. What would happen to the gases inside of you, if the pressure came off of you, is the gases would expand, just like they expanded in that can with the heat. But this time they would expand because there wasn't pressure on the outside of it.
How much time do you have without
0 seconds. Watch what happens. Do you want that to happen to your body?
Does he explode?
No. Watch what happens. What I'm going to do is I'm going to let the air back in. You ready? I'm going to let the air back in now.
We killed him. He did.
Okay,
We shot
let's try it again,
He
Laney.
died like Kennedy.
Oh, you can feel it.
He died like Kennedy.
We're going to try to boil one more time. Oh, that's just to show you it's aluminum.
Come on, actually doing rolling boil this time.
You coming out still? Yeah, a little bit. You feel it?
I think your vacuum chamber broke.
Maybe it is leaking. There it goes, there it goes. All right.
Told you.
Is that boiling?
Yeah.
Now, do you think the water's any hotter?
No.
It is not. So we did not add any heat. We just changed the pressure.
What would happen if you put the marshmallow in the water?
At different pressures, matter has different heating curves, different freezing points, and different boiling points. my equipment's not sophisticated enough to get this to happen. But you can actually get water to freeze, boil, and be liquid all at the same time. It's called the triple point. If you get the temperature just right and the pressure just right, water will do all three at once. Isn't that weird? I have no idea. Okay, you guys want to see one more marshmallow?
Yes.
Should I leave it in there with the water?
Yes.
All right.
What happens if you put the marshmallow in the water?
This one's just for. You guys want to do that?
Yes.
Yeah.
I want to see him boil.
We see them boil. Remember, it's not getting hotter. It's just bubbling. I don't know if it'll bubble. We'll see what happens. He's growing in the water, and it's going to make a mess, though, you guys. But I'll let the air back in. You guys want to let the air in? You guys say when to pull. Now?
No.
Oh, I thought it flew out. I thought it flew out the thing.
Okay,
was a good
guys.
idea.
All right, you guys. That is your demonstration for the day. Thank you very much.
Yeah.
I told you guys it was a good idea.